Okay, some notes on the magnetic field. Examples of field. The amount of gravity force per kilogram, if we put a mass there. So that's the ratio of gravitational force per mass. That's the first field we encounter in physics. The second is, and we just recently talked about this, the electric field. That's the electric force per coulomb. So that's in newtons per coulomb. And now finally, a third field, the magnetic field. That's B is the unit for magnetic field intensity. And that's a ratio of magnetic force to a charge, but also a velocity, since in order to experience a magnetic force, you have to be moving. Put that in the right spot here. There we go. So unit-wise, what have we got? We've got force units, so that's going to be newtons. Then we've got charge units, which is coulombs, and velocity units, which is meters per second. So that's a pretty unwieldy unit for magnetic field. So we call it something. We call that a Tesla, and use the capital T, named after Nikolai Tesla. Now, electric field is produced by static non-moving charges. To get a magnetic field, the charge actually has to move. So here are some typical sources of magnetic field. The Earth, there's circulating liquid iron and nickel and things like that moving through the core of the Earth. So we think that creates the Earth's magnetic field. Current flowing through a wire creates a magnetic field. Bar magnet, well, what's moving there? Well, I suppose it's the electrons zipping around the atom and creating magnetic moments there. Coil of wire, obviously current going through the wire there. And then the largest magnetic field we've ever created is in a tokamak, and that involves, again, a whole bunch of coils, but tremendous amounts of current flowing through the coils because this is bathed in liquid nitrogen, and the wires are superconducting, so they have no resistance, so you can run hundreds of amps through them and create a really large field. All right, so magnetic field patterns. Magnetic field is away from north and towards south. So that's a little bit like electric field, which was away from positive and towards negative. Now, compass needles will line up with the magnetic field, and we can drop little iron filings on top of a magnet to see the pattern as well. So first off, we've never actually observed magnetic monopoles. So we've never seen a single north by itself. But if we did, it would look like that. A single south by itself, we would have field lines coming in towards the south. But again, those have never been observed in nature. We think they exist because charge monopoles exist, but we've never managed to observe them. Okay, a dipole would be a single north and single south, and what that field pattern would look like would be north, south. Field lines would come out of the north. Let's try that again. Give myself a bit more room here. South, north. You can just superimpose this on the diagram. Field lines come out of the north and go into the south, out of the north into the south, away from north into south, away from north into south. So this would be the magnetic field pattern for a dipole. You just superimpose it there. Now, like poles will, of course, repel each other, and unlike poles will, of course, attract each other. Now, on the Earth, we know that a compass needle points to the Arctic, and we know, so there's the Arctic there, and we know that a compass lines up with the magnetic field, so we know the magnetic field's actually going in this direction. So this is the direction of the magnetic field here. It must be going to the North Pole. But we know that magnetic field lines point towards the South Magnetic Pole. So the North Geographic Pole up here must actually be a magnetic south. So if you were to superimpose a bar magnet on top of this, this would be south and this would be north. So this is the Arctic, it's the North Geographic Pole, but it's a magnetic south. Now we're interested in being able to calculate the field for simple geometries. The first one of interest is the straight wire. It turns out that the magnetic field for a wire is given by this expression. Mu naught, which is a magnetism constant, this is its value here, 4 pi times 10 to the minus 7, multiplied by the current in amperes, divided by 2 pi times the distance r, or d here, away from the wire. So this is how to calculate the magnetic field intensity for a wire. Now, I is, of course, the current, and that's in amperes, or amps, and r is the perpendicular distance from the wire. And that's going to be in meters. Oops, meters, there we are. And I misspelled perpendicular. There we are. Okay, now, the direction requires a bit of our attention because the direction is going to be tangent to a circle around the wire. We say the magnetic field curls around the wire. And this is the first of the famous right-hand rules in physics. What's the right-hand rule say? It says grab the wire with your right hand, thumb lined in the wire, current direction, your fingers show you the curl. So right here, with the current going to the left, you grab it so that with your right hand, your thumb points to the left, and observe the direction of your fingers curling. You see they're going up in the front of the wire and down in the back of the wire. So on top of that diagram, you can just superimpose this. So the curl is going to be going up in the front, and then it's going to be going down in the back. So that's the direction that the magnetic field is curling around that wire. If we have a current into the page, and again, you could just superimpose this on the diagram. Now we've got to stick our thumb in to the page, and that little X symbol means away from us. And if you do that with your right hand, you'll notice that your right hand fingers are curling in a clockwise direction. So the magnetic field pattern is curling around the wire in this way. And you can superimpose that on top, or here, maybe I'll just send it over here. Why not? Perfect. So this is the right-hand rule to find the field of a wire. Next, let us now take that wire and bend it into a loop. Now we see that there's current going to the left here. And again, you superimpose, I'll do it here. So current going to the left, that's right rather. So take your right hand, point your thumb in the direction of the current, and observe the curl. You should see the curl is coming down in the front, like that. And then if we follow this current all the way around the loop like this, and observe the curl, we see that in each case, the curl is sort of pointing into the page here. So the magnetic field B is into the page everywhere in this loop. And then when we get back outside, once again, it's going like this. So it's coming out at us here, and it's going away from us here, everywhere underneath the wire, and then everywhere in the center of this loop. So all those little fields are going to add up inside the loop and give you a really large field, okay? Now, on the outside, observe that this field from this little bit of current is actually coming towards you, but this field, because this wire will create field everywhere over here, this field is still going into the page. So there tends to be a cancellation of the field on the outside. We can repeat that over here. This field from this little bit of current is coming out towards us, but the field from this little bit of current everywhere on this side is going to be going away. So the field outside cancels, but the field inside adds together, so you get a nice big field at the center of that loop. So now, and you can just, again, superimpose that here. Now, let us add a whole bunch of loops together, and you get a coil. Now, if you put a core in, like a piece of iron or a nail, then it's called an electromagnet, and that enhances the magnetic field. And, of course, there's lots of applications for it. Now, it's helpful to do the following. The field is going to be strongest right here at the ends. And we see that the field lines are going in at this end and out at this end. So this reminds us quite a bit of a bar magnet, where we know the field lines come out of the north end and then go in at the south end. So this is going to be the south end of the electromagnet, and this is going to be the north end. Just by analogy with this bar magnet. Now, for the intensity of the magnetic field in a coil, it depends on, once again, the magnetism constant. It depends on the number of loops of wire and the current they're carrying. But if you stretch the coil out and don't pack the loops tightly, that makes the field smaller. Conversely, if you pack the coils in really tightly so that the coil's not very long, that makes the field much stronger. So there's inverse variation with the length of the coil. So there's the magnetic field intensity for a coil. And this, once again, is the current in amperes. This is the number of wire loops in the coil. That doesn't have any units. And this is the coil length, and that's in meters. Now, there's another right-hand rule to find the direction of the coil field. And this, once again, says grab the coil, but when you grab the coil, let your fingers go in the direction of the current. If your fingers go in the direction of the current with your right hand, you'll see these currents are going up in the back and down in the front. If you do that with your right hand, you'll see that your right hand thumb ends up pointing to the right. So these are the currents in the windings. The magnetic field is coming out at this end. That means it must be going in at this end. And here in the center, it's also going in a rightward direction. So this is the magnetic field direction for this coil. And you can just superimpose that. Here we have a coil in end view. So we imagine sort of holding onto a pop can and curling our fingers around the pop can. If you do that with your right hand in the direction of the current, you'll see that the field is actually coming up towards you. So make your right hand fingers go this way. Your thumb is going to point out at you. Out at you is a dot. So the magnetic field is out of the page here. And those are some preliminary comments on magnetic field, direction, as well as the field of a coil and field of a wire.